It's my privilege to tell a very brief story about our next presenter. We got the opportunity through meeting Dr. Carrie Cahoy at MIT at SmallSat just before COVID, and she invited our students to come to her lab and visit. And in her lab was a graduate student who has since become a new professor at Florida Tech. And she is here to present today. So it's my privilege to introduce Dr. Vale Pereira. Thank you.
Hi, everyone, and thank you for the kind introduction. It was very interesting. It was the first time that I gave a lab tour to middle schoolers, and it was like, wow, impressed. Hi, everyone. Thank you for being here. Today, I'm going to be talking about designing, assembling, testing, and operating CubeSats, and some practical perspectives that I've got through the years of working with them. And the first thing that I want to point out is the number of names that you see in there. And that's just to let you all know that satellites are very difficult to put together and to work on. So you cannot do it by one person. We always need a big team. So teamwork is key when working on satellites. So today I'll first talk a little bit about me, and then I'll give a brief overview of two different CubeSats, and then talk about assembly, integration, and testing, and my lab vision. So as Kevin introduced me, a Ph.D. student at MIT. When I first met him, and he's I did 2 undergrads in Brazil, a master's in Brazil, a Ph.D. at MIT, and now I'm finally at Florida Tech. And I just graduated about 4 months ago, 3-4 months ago, and I started as a professor assistant months ago. So the things that I'm going to be talking about in here today are things that are performed while I was a student at MIT. So just wanted to make that clear. So that's why I have the 2 logos up there. And while a PhD student in there, I was the lead mechanical engineer and assembly integration and testing lead for the BeverCube satellite, and also the lead mechanical engineer and lead operator for the DeMi satellite. So talking about DeMi. DeMi stands for the Deformable Mirror Demonstration Mission. That mission was a 6-unit CubeSat, so it was about 10 centimeters by 20 centimeters by 30 centimeters, 6-unit. And the big goal that we had in there was to get something called a deformable mirror and confirm that we can use one of those in orbit. And why would we want to do that? So when we are looking far away at stars that are not the sun, there are planets that orbit those stars. And we want to try to see those planets because we want to see if there is atmosphere, if there is life, if there is anything in there. So to see them, we need to block the light of the star, because if we don't, we only see the star and everything around it is so dimmed out by the light of the star. And the way that normally that's done is to do something called a coronagraph, which is placing a shadow, something in front of the star, so you can look at the planets around it. But the sad thing is that there is so much diffraction, refraction, and noise coming from that shadowy material that you end up having so much noise in your light that you cannot really see the planets, which is exactly what you wanted to see. And what we do on the ground is use adaptive optics or deformable mirrors to correct those light noises or light aberrations so we could see something far away. And that's the first image that you see there. That's Uranus without an adaptive optics and with an adaptive optics. And we know that on ground that is used quite frequently, but that's used in very, very big telescopes. Could we use that in a tiny telescope inside a CubeSat? So that's what we wanted to do, and that's why we designed and developed this CubeSat to do, to design and test and validate these deformable mirrors so we could look at planets orbiting other stars. And the deformable mirror that we used had 144 actuators, but it was about this size. So it was very tiny, and the actuators were very tiny. And the image that you see now is me besides the final version of the satellite about a week before we integrated it with the rocket and sent it to space. And talking about timelines, we started this project, the mission concept for this project in 2015. Then we got funding in 2016. We passed the preliminary design review in 2017. In 2018, we passed the critical design review. Then in 2019, we started the fabrication and all the integrations and delivered the satellite. In 2020, we launched and deployed from the International Space Station. In 2021, we did operations. And in 2022, we did operations and deorbited. The satellite burned down in the atmosphere last Pi Day. So it was sad. The next satellite that I worked on was BeaverCube. So BeaverCube was a 3-unit CubeSat, also at MIT, and I brought in here one of our engineering development units. This is one of the EDUs of BeaverCube. So BeaverCube was a 3-unit CubeSat, so 10 centimeters by 10 centimeters by 30 centimeters. And this CubeSat is very different than DeMi. And our goal on BeaverCube was twofold. The first one, we had 3 cameras, 2 infrared cameras, 1 visual spectrum camera, and we wanted to take pictures of the coast of the northeast side of the United States to track the color and the temperature of the surface of the ocean, because that area is being highly affected by climate change. And our second goal was to demonstrate a propulsion unit on board a CubeSat, because as we heard earlier today, there are not that many nanosats that have propulsion. And there is this company that developed one that could work. And so we partnered with them to use our satellite to test their propulsion unit. And here are just some drawings of what BeaverCube is on the inside, but you could also take a look and touch it later on. And the timeline for BeaverCube, we did the mission concept and requirements in 2018. We got funding in 2019. We passed the preliminary design review in 2019. Then in 2020, we passed the critical design review. In 2021, we did the fabrication and the assembly and integration and testing. In 2022, we delivered to NanoRex, which was our launch provider. Then NanoRex put it inside a SpaceX rocket, sent it to space, and it was launched in July 14 of this year. And we are currently in the operations phase, and BeaverCube will probably burn down in the atmosphere in 2023. So satellites go up and then come down. And so what I wanted to say today are just some things that I learned in that process of putting those 2 satellites together. So the first lesson is the difference between bus and payload. So a payload is what we actually want to do that will accomplish the mission. So in DeMi, the payload was the deformable mirror and all the optics around that deformable mirror. On BeaverCube, the payload were the cameras that were taking pictures of the coast, northeast coast of the United States. But for the payload to be able to do its job, there is a lot of things that are necessary. So the payload requires power. The payload requires a radio communication to the ground. We require a structure. We might require propulsion. And so all those things that are required for the payload to be able to do its job are called the bus. And it's very interesting how we can divide those 2, because there are many companies currently that provide buses. And so you can pick between doing the entire thing yourself or doing the payload and buying a bus and putting your payload inside a bus. And so now that we know the difference between those 2, the actual satellite design process, it starts with defining a mission. So the first thing that we need to know is, what are we going to do? And we really need to think a lot about that, because that's going to drive everything else that comes after. And when you have your mission inside your head and you're really sure of it, you write it down, you create a very beautiful presentation slide deck, and then you invite people from outside and they come in, they check your mission and they say, yeah, this is a solid mission and I think this can be accomplished. You're good to go. And this is called the mission concept review. And so after you pass the mission concept review, you start writing your requirements. The requirements are the things that you need to do to make sure you can accomplish the mission. So for example, for BeaverCube, for us to be able to accomplish the mission, we needed 3 cameras. So that was one of the requirements that came from the definition of the mission. And for DEMI, for example, we really needed a good pointing. So we needed a reaction wheel. That was something that came from the requirements. After you define the requirements, then you define your ConOps. ConOps is short for concept of operations. And your concept of operations is what you're going to do. So BeaverCube, it's going to point down to wherever the ground is when it's in orbit. Then it's going to turn on one of the cameras, take a picture, turn it off, turn on the other camera, take a picture, turn it off. And then on the next orbit, it's going to downlink all the information. And that process of what you're going to do and when is called the ConOps. And after you have defined your requirements and your ConOps, then again, you call people from outside, from industry, from other universities. They come in, they check your requirements, they check your ConOps in a very beautiful presentation, and they're like, yes, it makes sense, it's solid, you're good to go. And that's when you passed your requirements review, and you're finally going to component selection. So the first thing that you do is selecting the components for your payload, the things that are actually going to accomplish your mission. And after you do that, you have to make sure you're following SWAPC. SWAPC stands for size, weight, and power. And then later, the C was added for cost. So there is an A for end, but the end is not at the end. It's funny, but it's size, weight, and power, and cost. And you have to make sure that those things are being inside your budget. So your budget for mass, your budget for size, your budget for price, your budget for power. And that is also very interesting that you need to take a look at one thing called NASA GAVs, and that's just standard environmental conditions that NASA has told you that space is going to be. And so you make sure that you follow and you make something that will survive space. And after you have all that, then you finally select your bus, either from a company or from you going to make your own bus. And when you have that done, you go back to the requirements to make sure that you're really achieving all the requirements that you wanted to achieve. Okay, good. And what if, after all this is done, you're like, oh, but I really wanted to do that thing too? Things get messy, because then if you change the ConOps, then you have to go back and change the requirements. And after changing the requirements, you also have to change the components that you selected to do the mission. And with that, you also have to redo all the calculations for size, weight, and power, because you have new components. And with those new components, you might also need to do a new bus or select a new bus. And with that new bus, you also have to check again to see if the requirements are being met. So, the hard way, I learned that after you have the requirements and the ConOps set, you do your best not to change it. So that was one big lesson. And after you have all this done, all this process, then you're finally going to do what is normally called design, which is opening SolidWorks or whatever CAD tool you use, doing a CAD, doing the mechanisms, doing the calculations, and being with a 3D model of your satellite in front of you in a screen of a computer. And after you do that, then you do analysis to make sure you're going to withstand vibration and temperature environments and your orbital parameters and etc. And then after that, you do some prototypings and some engineering development units, just like the one that I showed you here for BeaverCube. And then after you have all these done, you're finally going to the very, very fun part, which is the assembly, integration, and testing. The assembly for satellites is normally done inside clean room. So it's not the best condition to be for many hours, but that's what happens. You stay in there for many hours doing fit checks and checking all your prototypes and putting everything together. And when doing fit checks and when doing designs, remember that and when you're talking about CubeSats are small and you're trying volume, and sometimes you forget that you need a there. So have that in mind, and you might only realize that when you're doing fit checks. So fit checks are important. And then after you have that done, you go to your environmental testing, which is going to the thermal testing to make sure you're going to survive the temperatures in orbit, thermal vacuum testing to make sure you also survive the vacuum in orbit, and then the vibration testing to make sure you can survive all that shake that the rocket's going to put in your satellite. And that's when you're finally like, Good, because you have everything assembled. You went to the first stages of assembling, the testing, the functional testing. You finished all the assembling with the bus and the integration. And the last picture there on the your right is BeaverCube being integrated with a deployer from NanoRacks, which was the company that put us inside a rocket and sent us through space. And that's like the entire process in a very short overview. And after all that, all these things that I've been talking about, I've done while I was a PhD student at MIT. But now I'm no longer in there. Now I'm at Florida Tech, and I want to continue doing those things. I have a lab vision that I want to continue developing instruments and models for the deep space exploration, bringing humankind closer to finding whether or not we are alone in the universe, and to extend our presence in deep space while ensuring we use in situ resources responsibly and efficiently. And for that, I really want to continue doing CubeSats because they are important features and important stages in deep space exploration. So small satellites are very important, and I hope you learned something today about how to make satellites. If you have any questions, feel free to reach out to me. And I love this picture because it's someone with a carry-on luggage on an airplane taking a satellite as carry-on luggage. And I think that that was just amazing. But thank you all for the attention.
Thank you so much. Great talk. So those of us in South Florida are very fortunate to have a professor like Dr. Dobel Pereira this close to us so that we can get great advice and learn from her. So thank you. Several years ago, I had a great opportunity to pick some high school freshmen to be the first kids to fly on something called Zero G. When we were there, I met this fellow named Peter Diamandis. He's called a futurist. He's got a great backstory, but he had been a co-founder of Zero G. And also, apparently, when he was an undergrad, I think at MIT or Harvard, he and a couple of friends, they started this organization called Students for the Exploration and Development of Space. I have met some wonderful SEDS college kids over the years, college students, and we're really happy to have a representative here at the national level of SEDS. So it's my privilege now to introduce Miss Harper Cheyenne.
Hi. So I've been involved with SED USA for the last 3 years. I originally started in diversity and inclusion at the internal level within our organization. And then I was elected vice chair of the national organization. And then I started working for this diversity and space CubeSat project, which is really at the early stages of development. I've been in the professional realm now for about a year. I'm a systems engineer for propellants out here at Cannady Space Center, which is completely different from being involved with a CubeSat project, but my heart is in it because I have a physics background. So for me to say, I really want to be an engineer, how do I do that? And then to transition to being an engineer, it was 100% because I had my hands on some projects. And so at the national level, I'm trying to make sure that that happens, that we have a good support system, that we have the money, and that we have a really solid team. And by the way, feel free to contact me for anything regarding this presentation or not, because like I said, I've worked at the overall level for a while now. So we're working on, like I said, the Diversity in Space CubeSat project, and we're involving members from not just SEDS USA, which SEDS stands for the Students for the Exploration and Development of Space. It is a mouthful. But we're involving AIAA, NSBE, SHIP, and SWE. because especially as we enter the workplace, we realize that we're not just working with SEDS folks, we're working with AIAA, SHIPS, NSBE, all of these different organizations. So the idea is to make sure that we're all working together and we all enter the workforce with the skills we need, the community we need to actually succeed. So we're hoping to build a 1U or a 2U CubeSat over these next few years. And with our connections that we have at the national level, we've worked with Mike Kincaid from NASA. We've worked with folks from Blue Origin, from SpaceX, all over the industry. So we're really envisioning this as a success. We're starting this project in Texas right now. We've been talking to universities in Texas, but we really want to engage folks from not just Texas, but elsewhere and see what the feedback is. If y'all are really engaged in doing something like this and we have the resources, we would like to go ahead and engage as many folks as possible. The start of this project is in quarter 4 of 2022, so in the next couple of months, and then running through quarter 4 of 2026. We've been given that estimate from people in the industry, but we understand that those things can change, development can change, plans can in general change. This is funded if you are at the student level and you're getting involved with this project. Like I said, if you're from AIAA, NSBE, SHIPS, SWE, or SEDS, you will not be required to pay anything into this project. We will fund that for you. We really want you to get the experience and, like I said, to get into the industry. This project, right now we're narrowing down what the idea is for the data we're going to collect, but we want to pull on some of the EU, the European Union sustainability goals. There are 17 of them. They involve things like eliminating poverty, looking at clean water resources, things like that. So we do want to involve sustainability goals in this and get not just folks who are interested in engineering, but perhaps there are people in agriculture, artists as well, who want to be in this project because, like I said, it has a very overarching scope that can involve a lot of different students. I also wanted to talk about high school involvement here because I know there are a lot of high schoolers. SEDS is not just involved at the college level. It primarily is. You probably have a local chapter if you are a college student here. But at the high school level, we also engage students. We're hoping to involve students with this project long-term, getting their hands on it, but also having maybe some speaker series, some webinars that high school students can attend virtually and learn and listen from folks who are in the industry. For a high school student group to be involved, you just need 3 starter members and a faculty member who's willing to lend a hand, help you figure out where your meeting space is, but also to really engage y'all in projects, in networking, whatever it is that you want to do. SEDS is not a group that has like a requirements list. So if you want to be a chapter and you're just interested in space, you absolutely can. Our chapters are each very diverse across the United States. We even, although I'm from SEDS USA, we have SEDS chapters all around the globe. We have a group called SEDS Earth. So even though it started at MIT by Peter Diamandis, it has certainly grown to larger proportions. But if you're a high school student who wants to be involved, contact Sarah Alvarado at seds.org. She will help you navigate this process. She will help you figure out how to engage your school, get a letter to your principal, all those great things. We are a nonprofit organization, and it is absolutely free for high school chapters. We want to engage you before the college level, and in order for us to do that, we need to make it free. That way, anyone can be involved. I'm going to go back to the first slide really quick. Like I said, that is my contact information. If you have questions on what I've said here or really anything within the organization, If I don't know the answer to it, I will send you to the person with the answer to your question. So thank you for having me.
We have one more presentation for today. So space is infinite, but the aerospace community is actually smaller than you think. So once you start doing aerospace, even if you're a young student, before you know it, you'll have built a network that's folks in other countries, other industries and whatnot. And this is a great story. So I actually don't know how I met Greg Cannady, but he's involved with our next presentation. I'd like to introduce One Voice for Change, which is a really good nonprofit that's based out of Colorado. So I'm going to invite up the CEO. I'm going to invite up the CEO, Felicity Muench, and a special guest from Peru. And Mr. Greg Cannady will be one of our virtual presenters from Colorado today. So Ms. Felicity, come on up.
Thank you, Greg. I will let you begin. This is Dr. Greg Cannady, COO of One Voice for Change.
Hey, hello, everybody. It's so nice to be here today. I really want to start off by thanking Kevin and all the work that he's done to inspire us for years around education and CubeSat. So thank you, Kevin. Thank you, BeverCube Aerospace. And you can see all the other partners involved in this amazing announcement today. SteamWorld from Peru. We're having mentors from the United States Air Force Academy, STEM Outreach, Society for Hispanic Engineers will be helping us mentor, and SwarmX from several universities around. And then our Peruvian friends are on virtually as well with us today, and they'll get to speak in just a second. We also, of course, want to thank Workaway International for sponsoring this project. Our approach is really simple with One Voice for Change. We listen to students, listen to industry, do something meaningful together, which we hope empowers everybody on all sides. I'm going to turn it over to William Mayville right now from Wolfpack CubeSat Development Team and BeverCube Aerospace. William, it's all yours.
Thank you, Dr. Cannady. Good afternoon. It's great to be here with all of you at the first annual SmallSat Education Conference. However, what's even more exciting is what I am here to talk about today. Before that, I'd like to discuss how I first began working with Mr. Simmons. I started out as a student of his when I was in the 5th grade. And as part of my experience in Mr. Simmons' aerospace programs, I was able to work on a number of missions, many of which have since been launched or are scheduled to be launched, as well as write papers and present at a number of conferences around the world, such as this one. However, now I've started a nonprofit called the Wolfpack Orbital Launch Funding Competition, a subsection of the Wolfpack CubeSat Development Team. And my goal is to help other students around the world have access to the same opportunities that I had access to. As such, I'm very pleased to announce the partnership between the WCDT and by extension the WolfC here with One Voice for Change. We have allowed we've allowed 15 teams of secondary level students in Peru to acquire a CubeSat emulator kits, which they will use to develop hands-on educational experiences with SmallSat technology. However, the reason why this program is so exciting isn't because of what it is, it's because of what we expect that it will grow to be. We see that this is simply the pilot program for what we hope to be a much larger program, which we'll be able to formally announce next year, involving hundreds of teams and hundreds of students around the world, ranging from a number of countries in Latin America, as well as Africa. Now I'd like to introduce two special guests, Mr. Cesar Ojeda a STEM educator and instructor from Peru, as well as Paula Wong, an engineer, as well as the president of STEAM World, a STEM education organization in Peru. Thank you.
Hi. I want to start this speech saying thank you. Thank you very much. My name is Cesar Adrian Ojeda Flores, and I am a teacher, a principal in a school in Peru. I come from Peru. This school is in the middle of the rainforest in the Amazon River. I don't know if you stay there. No? No. You are invited to visit. Okay. I say thank you because you are here. Yesterday I was there. But these great people is opening the opportunity to be a better world. The scientists said that the rainforest, the Amazon jungle, is the lung of the world. Are you agree? Yeah, that's right. I am living there, and I see how we contaminate this part of the world. I'm not sure, we are not now how care the land of the world. Okay, what do we need? We need to know, we need to want, and we need to do. And I said, thank you, because you are opening the opportunity to know how to do, to want to do, and to do. For example, these small satellites, the inspiration to my students is, this is the problem. We are contaminating, what is the word? The river with plastic, heavy metals, a lot of things. This river ends in the ocean. We are contaminating the ocean. And in my place, we can control this. What is the problem? It's the opportunity to solve this problem. Well, satellites. We will build satellites to know how we can solve this problem. My students are very, very interesting and exciting, and I want to say hello to them. They are here listening to me now, and I want to finish to say again, thank you very much. To open this opportunity, a lot of people that want to solve the problems. And more, if we build better persons, we will have a better world. We are doing this. The first step is here. The satellites is the opportunity. And I am here, a voice to change the world. Again, thank you very much.
I believe we are ready for Paula and her students in Peru.
Hello, I am Paula from Peru. I am the coordinator here in Peru. I am Peruvian, and I just want to take some seconds to say that we are really excited just to start with this wonderful project. All the Peruvian teams are connecting now, watching the part in this for this moment. So I just want to say that Cesar said that thank you very much. This is a great opportunity. I know that space technology is a big tool for the humankind, and we will do a great things with this project. And thank you very much.
Thank you. In order to know what to do in the future, we have to use our imagination. And it takes an incredible, creative, imaginative world mind to create the future. So let's start now. Imagine a future where students globally are given the opportunities and support that we are seeing in this groundbreaking collaborative project with Peru. If anyone asked me to define hope, or what does hope look like, I would say look into the eyes of every one of you that is imagining the future and making a change for the better. This project would not have happened without the support of Workaway International. Thank you. The tremendous work of William, incredible, thank you. STEAM World in Peru, the Society of Hispanic Professional Engineers, the United States Air Force, James Moore, Engitronic, SwarmX, BlueCube Aerospace, SmallSat Conference, Cesar, and Paola. And in closing, I would like to say, one voice can change the world. Just one voice can change the entire world. All of you are the voice changing the world for good. Thank you very much. Thank you.
I want to thank you all for being here today. This actually concludes day one of the SmallSat Education Conference. I want to invite you again. Tomorrow we have a great lineup of speakers, beginning with Dr. Jen Kang of the U.S. Naval Academy, first thing in the morning at 9:30. Please be safe traveling. If you're going to the banquet, I will see you soon. And thank you all very much for being here today. See you tomorrow. Excuse me, we're going to draw the raffle for the Elegoo 3D printer now. I'll hold the bag for Mr. Johnson.
All right. So folks, before you exit, as Kevin mentioned, we are doing the raffle drawing as we speak. I do want to thank our sponsor, Elegoo, who shipped us a 3D printer in order to give out to this event. If you haven't had a chance, please take a look at it. And without looking and very carefully selecting a ticket, the winning number is 929098.
What?
929098. Excellent.
Let's verify the ticket.
Congratulations. Would you like?
Cool. Tennessee. Welcome.
Would you like to? We're gonna need to get a photo of you next to us.